Hi, welcome to Module 3 of a brief introduction to game theory. In this module, we're going to start talking about game theory proper, which involves the play of not just one person, one actor trying to take an optimal action, but rather multiple actors who are simultaneously trying to decide upon actions or strategies that are optimal, conditioned on everyone else's behavior. The first kind of setting we're going to discuss is the setting of a simultaneous game. A simultaneous game is a particular kind of system in which two or more actors have to decide upon actions at the same time, simultaneously. Because there's simultaneous play or simultaneous actions taken, each actor can't know ahead of time what the other actor has done already with certainty. So if you and I decide at the same time whether or not we want to cooperate on some action or defect from cooperation, we won't know ahead of time what the other person is actually going to do, so we have to kind of guess. That guessing is fundamental to game theory in a sense, and we call it counterfactual thinking. A counterfactual is literally counter to fact. It's an imaginary world that we posit, that we sort of propose to help us understand and think through what we should do given possible alternative behaviors from other people. Or other actors, sorry. I keep saying people because it's easy, but remember, actors can be anything. Okay, in your model. So what does that mean? Well, let's say I'm playing a game of cooperation with you, and we'll discuss that game in more depth in this module. But let's say I'm playing a game of cooperation with you, and I have to decide what to do. Should I cooperate or defect? Well, I'm going to think counterfactually. I'm going to imagine worlds in which you cooperate, and then I'm going to think about what I should do in that case. Then I'm going to imagine alternative worlds in which you defect, and then I'm going to think about what I should do in that case. If I do that, then I've put the question a little differently into situations in which I'm deciding what I should do given a series of your possible actions, and for each one of them, what I should do. That's known as a best response. A best response captures my rational response to each one of the things that you could do. So again, the counterfactual world is you are cooperating. I'm imagining a world in which you cooperate. Then I have to consider what's my best response, what gets me the best outcome if you are cooperating. Now I have to consider the possibility that you're defecting, that counterfactual world. And then I think, okay, what gets me the best outcome for me if you're defecting? Once I've done that for everything you might do, to figure out what I should do in that case, all I have then to figure out is what's the chance that you cooperate and what's the chance that you defect, and I can consider my expected utility for cooperating or for defecting, and I can figure out what's the optimal thing for me to do. But it all begins with assessing best responses, which is given you're doing something, given you're cooperating, or given you're defecting, given you're choosing A or B or C, what's the best thing among my actions, among my strategies, that I can do? And that's a best response. It's a rational response to other actions. And it's fundamental to all the stuff we do in game theory. Make sure you got that before going on, because that's an important concept, the best response. It's sort of, as I said, fundamental to game theory. Once you get that, everything else follows pretty directly. And the first, and it follows in the sense that once everyone is playing best responses to everyone else's actions, we can end up with what we call an equilibrium, or equilibrium behavior. Equilibrium behavior is behavior such that everyone is playing best responses to everyone else, and therefore has no incentive to change to some other behavior. So for instance, if in this game, if my defection is a best response to your defection, and your defection is a best response to my defection, then we are both independently and individually playing the best thing we can play given the other's actions. Given that, neither of us have any incentive to deviate to some other action or to change our actions. And that's another way of defining equilibrium here, is that no one has a beneficial deviation from their equilibrium play or equilibrium actions. If we're both playing defect, and we both have, and that's our best response to the other player's defect, then any changes one of us might make Any deviations, any switches in strategy that I might make will only leave me worse off than I was when I was playing Defect. That's any unilateral deviations. So we can define, and we call it Nash equilibrium after John Nash, mathematician slash early economist, not really, I guess, economist, and there's two different ways to define this, I said. One way of defining this Nash equilibrium play is that all players play best responses. All actors are taking the actions that provide the best outcomes given the other player's equilibrium actions. We can also define that as no one has a beneficial deviation from equilibrium play. These are equivalent definitions. They're differently useful in different contexts. For most of what we do in this class, the second definition, that no one has a beneficial deviation, is going to be the more useful definition. Okay, so that's all definitions here. Now I want to go through a bunch of examples to show you how we set up games, why we set up games the way we do, what they can tell us, and more directly to this module, how to actually go about solving for equilibria of simultaneous games. Okay, so I'm going to start with probably the most famous, most commonly seen game, The Prisoner's Dilemma, or PD. The Prisoner's Dilemma stems from a story. It's a kind of odd story, but the story is this. You have two prisoners who are being interrogated. If they both refuse to cooperate with the interrogation, then they both do pretty well. They both do quite well, actually, because the people interrogating them lack the information needed in order to prosecute them. So we assign payoffs to this. So the outcome of having not enough information to prosecute is one the actors like. And so we're going to assign a particular payoff value to this. We're going to assign a 2 in this case. The number we assign is arbitrary. In this case, what's going to matter is the order of the numbers. Because utilities, the higher utility you have, the more you prefer that outcome. So as long as we assign an appropriately ordered utility set, then for any game like this, in which there's no uncertainty, it's equivalent. So we're going to start off with a PD here. I'll write PD over here. And we're going to start off with, and we're going to write this out using what's called like a game matrix. And this is a convenient way of writing all the outcomes given the strategy combinations. We have two actors. We'll call it actor 1 and 2. In general, these actors can be very different, but for these games, we're going to assume both actors are identical to make life easy. So, what's a PD here? Well, you have two different strategies. There's a strategy of cooperation with each other, not with the interrogators. So, cooperation with each other, or defect against the other one. And each actor will have those pair of strategies. Because each actor has two possible strategies, there are 4 possible outcomes for each combination of strategies from each actor. The first one we just dealt with was both actors cooperate with each other, so they do not rat out the other one, and in that case, they both do pretty well. I'm going to assign kind of arbitrarily payoffs of 2 for each actor. 2, 2 means the first actor gets the first 2 payoff, and the second actor gets the second 2 payoff. In this case, the actor with the strategies in the rows, cooperate or defect, gets the first payoff, and the actor with the strategies in the columns gets the second payoff. Now, what happens if they both rat out each other, right? If they both provide information that harms the other one? Well, they both do worse than the case when they both fail to provide information, and the interrogators can use the information against them. In this case, I'm going to assign a 1-1. Now, that's not very much different than 2-2, but again, it doesn't matter. 1 is less than 2, so it's okay. Now, what happens if only one of them rats out the other? What if one of them cooperates with the other actor and says nothing, but the other one spills the beans, right? Gives all the information away. What happens then? We're going to say the one who rats out the other gets rewarded for that by the interrogators. So we're going to say they get a 3 in that case. So they get even more than they could when they both cooperate. They get a bonus for doing that. They don't get punished themselves, and they get some kind of bonus, some reward. And same is true over here. If the second actor is the one who does this, then the column payoff here, the second payoff is 3. Now, what happens if you're the one who cooperates with your fellow, but you get ratted out? Well, in that case, we can say that's the worst payoff possible. That's the payoff in which you get a 0 because you suffer all the costs of having information given away about you and none of the benefits. So you suffer the maximum penalty. 0. Okay, so here's our setup for the prisoner's dilemma. This is the setup that's designed to fit a particular story, but it's more general than this. We actually can set it up so that we change the names of these things. So, for instance, if we set it up for cooperate for the RR for reward, that's the reward payoff for cooperation. If they both fail to cooperate, we use PP for punishment, so both actors get a P. If only one actor, if the actor who defects, but the other actor is still cooperating, that's a T for temptation. It's the extra bonus you're tempted with to avoid your cooperation. Let me put that here as well. And then if you are the good actor and the other actor defects against you, then we call it S for sucker's payoff. Sort of rude, but that's how it's generally set up. These payoffs are very general as long as T is greater than greater than R is greater than P is greater than S. There's one more notation, one more assumption that's often used, but I'll leave that out for now. As long as that ordering holds, we have a prisoner's dilemma, and it applies to any game in which it's collectively beneficial to cooperate and get the reward, but there's individual incentives to defect to get the temptation payoff, and then a worse outcome, as we'll see, occurs. Okay, so here's a setup for the prisoner's dilemma. How do we find an equilibrium? Well, the way we do this for this game and for all the games we're going to see is exactly the same. And what it is to consider what your best response is to every action your opponent, or your partner in this case, might play. So let's consider that. Let's consider player 1 first. So we're over here with player 1. What are the two possible actions that player 2 can take? Well, player 2 can cooperate, or player 2 can defect. So let's compare player 1's payoffs in both cases. So let's say player 2 is cooperating. We're going to exist in a counterfactual world, an imaginary world, in which we know with certainty player 2 is cooperating. What's our best response to cooperation in that case? Well, let's look at our payoffs. A best response is always the response that gives you the best possible outcome. So if I cooperate, I get a 2 payoff. If I defect, I get a 3 payoff. Because 3 is bigger than 2, it's always beneficial for me to defect instead of cooperate if my opponent or my partner is cooperating. So to show that, I'm going to put a little underline below the 3 here to show me that this is what I should be doing. Now, what happens if instead I know with certainty in this counterfactual world that my opponent, my partner, is defecting? What should I do then? Well, again, I compare my payoffs. I get a 0 if I cooperate, right? That's the sucker's payoff. Or I get a 1 if I defect, the punishment payoff. Well, punishment aside, it's still better than being a sucker in this case, so I get a 1. So now, what I'm finding is, if I'm player 1, regardless of what my opponent's doing, whether or not my opponent cooperates or defects, it is always better for me to defect. We say in that case that defect in this game, in the PD, is a dominant strategy. Defect here is dominant. Okay. Defecting is a dominant strategy because it dominates all other things I could do. It is always better regardless of what my opponent does. I should always defect. Okay. So that's me. What about player 2? Now you might guess that player 2 is the same as player 1, so it probably should be the same, and it is, but let's just work through it. So player 2, now we're going to assume player 1 lives in 2 different counterfactual worlds, one in which player 1 always cooperates, one in which player 1 always defects. And we're going to see what player 2 should do. Well, if player 1 always cooperates, we're going to compare the column payoffs, the second payoff for player 2, and we're going to compare 2 to 3. Now 3 is better than 2, so player 2 should always defect if player 1 cooperates. Now over here, we look again, and we see what if player 1 always defects? What should player 2 do? Well, player 2 is now going to compare 0 to 1. 1 is better than 0, so player 2 should always defect. And again, as we expected, we're finding that for player 2 as well, defection is a dominant strategy. Player 2 always has the best response to play defect, regardless of what player 1 does. Now we've done that for we've found best responses for every possible strategy of the other player, we're done. What's the equilibrium? The equilibrium is when both players are playing a best response. In this case, it's any cell in this game matrix in which you have both payoffs underlined. And here it is the lower right one, where both players defect. Because once both players defect, neither player has a beneficial deviation. To see that, let's say they're both defecting. Player 1 can then cooperate unilaterally and get a 0. That's worse, so player 1 won't do that. Player 2 could cooperate unilaterally and get a 0. That's worse, so player 2 won't do that. So in this case, neither player has incentive to deviate. Now, a natural thing to say here is, well, but they can both get 2 if they just both cooperated. Why can't they do that? Well, with the game, we consider unilateral deviations, no beneficial unilateral deviations from equilibrium play. So by the rules of equilibrium, we can't simultaneously agree to go to 2 at the same time. That said, though, how would that work? Well, let's say we both were starting at 2 and at cooperation. Let's say we're starting up here. What would happen? Well, both players would have incentives, individual incentives, to deviate to defection to secure a 3 instead of 2. Because if we both started at cooperation, and then I, on my own, defect, I increase my payoff from 2 to 3, I'm better off, I get a higher utility, so I must prefer to do that, so I will defect from this nice cooperative equilibrium. You will feel the same way and defect as well, and because we both defect, thinking we will get the 3, we'll get 1 instead. Can we stop that? No. Because as much as I can tell you, look, no, I will definitely cooperate. You should cooperate because I will definitely do that. Once it's my turn to act, right? Once it's my turn to act, I'm going to defect anyway because it's better for me individually. And you'll know that because you'll know I'm rational, and so you won't trust me to cooperate. And because I know that you won't trust me to cooperate, you'll defect as well. I should defect off the bat because I know you'll be defecting. And you know I know that, and I know you know that, I know that, you know that, I know, and so on and so forth forever. And game theory involves this infinite regress of common knowledge. That I know that you're rational, and you know that I'm rational, and I know that you know that I'm rational, and I know that you know that I know that you know that I'm rational, and so on and so forth indefinitely, and I probably missed one of those. But it goes on forever like that. We all know what we're all going to do in equilibrium because we must do those things because we've all solved this game. We've all thought rationally through our outcomes, devised our best responses, and figured out what the optimum strategy was to do. So that's how this all works. And you solve all these games the same way. So I'm going to go through a couple more to give you examples of different intuitions you acquire from games, but they're all solved in the exact same way, as we'll see. Again, the point of the prisoner's dilemma is to capture scenarios in which you have benefits from cooperation, from joint cooperation, but individual incentives to fail to cooperate. A common example of that people see every day is when you live with someone else, right? You all benefit from having a nice, clean living space, but you all have individual incentives not to clean because you get the time for yourself. And if someone else cleans it for you, you get the benefit of the clean room and don't have to do anything yourselves. You save time. That likely seems awful. I hope it seems awful. But the idea is that the incentives exist to deviate. You might say, well, my incentives are to cooperate because I get a benefit from cooperation because I feel good about that. That's great, and that's likely, and we're going to get to that explicitly later in this series of modules. Later in this lecture, we're going to discuss altruism and other regarding preferences. That is often considered behavioral game theory because it changes incentives. In this case, all that would mean is you can change the payoffs. If I change these 2s to 3s up here, so for instance, if these 2s became 3s and these 3s became 2s, suddenly it's totally fine to cooperate because 3 is the highest payoff, and if we're both cooperating, there's no incentive to deviate. So one way to make this game work better for people is if you just change the payoff so everyone really loved cooperating, and then there'd be cooperation potentially with no worries. That said, defection would still be in equilibrium in that modified game. And just to make it clear, the modified game I'm talking about looks kind of like this. In that case, if you go through the same exercise we did before, you would have these underlined, and you can try it at home yourself to make sure you can do that. And then if you have two equilibrium, you can either have both players defecting or both players cooperating. That's what we call a multiple equilibrium setting. We'll talk about that a little more later, but game theory does not specify which one both players do. It just says both of these are possible equilibria because there's no incentive to deviate from either one. Okay, so that's the PD, and that's probably the most famous one in terms of games like this, only because there are lots of scenarios we think happen in the real world in which both players would benefit from cooperating but have individual incentives to defect. This happens all the time if you're studying, say, international relations, and you have multiple countries, multiple nation states, that have incentive to cooperate on some joint agreement, but there's individual incentives to deviate from that. Or you're dealing with some kind of common goods problem in which you all want to take advantage of this nice park, and you all benefit from having this park clean, but you have an incentive not to go to the garbage can, you have an incentive to just dump your garbage wherever. If you just do it by yourself, the park is still pretty clean, and you save yourself some time, so that's your incentive to deviate. But everyone has that incentive, so the park ends up kind of crummy. There are lots of examples like this that can be either naturally applied to a prisoner's dilemma or shoehorned into a prisoner's dilemma that you might see them in the literature. But we're going to stop there for now and talk about some other common problems. The next one, as a common example, is a coordination problem. Coordination problems look kind of like this, and this is just one of possible example of many. In a coordination problem, both actors, 1 and 2, have two actions, A and B. A and B can be anything. So if, say, we're trying to meet somewhere, it's a common coordination problem. So let's say we say, hey, let's go to New York City and meet somewhere. Of course, New York City is very big, and having not specified where to meet, how we know where to meet? Of course, now everyone has a cell phone, so whatever, it's easy, but back when these games were made up, it was hard. So the idea is, how do we know where to meet? We set up payoffs like this because it doesn't matter where we meet. All that matters is you are together. So if we both end up at site A, we choose A, and we both end up there, we both get a payoff of 1, and we're happy. If we both end up at site B, we both get a payoff of 1, and we're happy. If we're in different places, we're both unhappy. That's a coordination game. A coordination game is just one where we want to coordinate on some action or actions. So in this case, we can go through and do the same exercise as before and say, okay, what's the best response? Well, and you should do this again at home to make sure you can do it. But again, if they choose A, I want to choose A. If they choose B, I want to choose B. Similarly, if I choose A, they want to choose A. And if I choose B, they want to choose B. So there are two equilibrium. Both choosing A or both choosing B is an equilibrium. That doesn't really solve our problems, right? And this is what I meant when I said I'll talk about multiple equilibrium in a second. If we have multiple equilibria, we don't actually have any predictions for what's going to happen in the game, right? They could both go to A, they could both go to B. Both are fine. One solution to that problem we'll talk about later is to choose at random. Maybe choose a half chance of going to A and a half chance of going to B. Then 1/4 of the time you end up both at A, and 1/4 of the time you end up both at B, and another half you end up in the opposite places and being happy. That's a solution. Not a great solution, but it's a solution. A better solution is to make the game broader and have some prior play to the game we just discussed in which you talk about it. That's the easiest solution. That's not possible in this game because we've specified the game only exists as one simultaneous move to choose where to go. But in real life, there's often prior moves that exist to coordinate on stuff. A common solution to this kind of problem put forth originally by Thomas Schelling, was that there's a focal equilibria. Maybe A is Times Square and B is some random coffee shop that you've never heard of before. In that case, A is a focal equilibrium. We all think of Times Square as synonymous in some cases with New York City, whereas that random coffee shop that only you've heard of is not so synonymous. So the focal one, the natural one to think about to coordinate is A. We'll both think that and end up there naturally. That's a potential solution, but it depends a lot upon common knowledge and common beliefs about what's focal. Okay. This is a coordination game. There are many variants of these things that don't change anything. So let's say we both preferred that coffee shop. Times Square is busy and noisy, whatever, and we don't want to go there. So we want to go to the coffee shop, and we may get a better payoff from there. That changes nothing. The equilibrium is the equilibria are the same. You could end up with this equilibria or this equilibria, and you don't know which one you end up at. You might think, well, of course we both go to the coffee shop because it's better. We get a better payoff. So maybe that's focal now. But again, the game theory itself doesn't tell you which one you go to, because the game theory says you will coordinate on one of those two. Those are equilibria. Those are possible equilibria. So you could coordinate on one of those two, or you could choose randomly. But which one you coordinate on is not really determined by the game that we presented. A third common game was originally called Battle of the Sexes. It was super sexist. Various versions of it later have changed it to other things like Bach or Stravinsky preferences you have. The idea is this. It's a coordination game again, but now the players have different preferences. So player 2 prefers choice A, and player 1 prefers choice B. Again, they both rather be together, but the players prefer opposite actions. What happens there? Same idea, same way to analyze, same two equilibria. Which one do they choose? I don't know. You need some extra parts of the game to figure out which of these two you end up choosing in practice. All game theory says is there's two possible equilibria. Okay. Another one. Let's do chicken. So this is I'll erase these to make it easier to see. Okay. So how about chicken? Chicken's another kind of game in which you have these kind of payoffs, and I'll go through why they exist in a second. Chicken's usually used as swerve or not swerve. So the game of chicken is a game in which you both drive cars at each other. And you can either swerve or not swerve. Okay. Oh, sorry, I wrote this too big. Let me do this over again because this is too big. Hold on. Okay, so swerve, not swerve, swerve, not swerve. Okay, if you both don't swerve, that's the worst outcome. You both crash, bad things happen. So let's put the worst possible outcome there at 0. Again, I can make this negative 1 billion, but who cares? 0 is the lowest payoff I'm going to use, so that's fine in this case. Now let's say you both swerve. Well, that's a decent payoff. You both survive. That's great. And since you both swerved, no one's really mocked for not being cool enough to drive your cars at each other. Again, these are games often remaining like the 50s, so there you go. 60s? I don't know, actually. Early. So, maybe earlier. So, now what happens if I, player 1, don't swerve, and they swerve? Well, I get the best benefit there because I've shown how awesomely brave I am by driving my car at someone else. Again, I don't know. But I get a 3 for that. They, however, have swerved and get a 1. They're still alive, which is great. But, they're not hurt, which is great. But they also have shown themselves to not be as brave as I am. Whatever. Anyway, same thing reverse over here. What are the equilibria? Well, again, we can go through a chicken game and figure out what the equilibria are. The same process. If player 2 swerves, what should I do? Well, 3 is better than 2, so I should not swerve. If player 2 does not swerve, what should I do? Well, 1 is better than 0, so I should swerve. So in a chicken game, I should do the opposite of what my opponent does. What about my opponent? Same deal. If I swerve, I'm comparing a 2 to a 3, so I should not swerve. If player 1 doesn't swerve, I'm comparing a 1 to a 0, so I should swerve. We have two equilibria. Just like for a coordination game, we have more than one equilibria. However, more than equilibrium, but however, in this case, they're opposite. Each player must do the opposite of their opponent. How do you figure out who chooses to swerve? I don't know. Again, as with all multiple equilibria scenarios, I can't tell you up front what we should do. Who should choose to swerve? One of us should swerve. Which one is, I don't know. Okay. That's a chicken game. It's meant to model situations in which we both have incentives to keep going for something, right? But if we both keep going, right, disaster happens. So someone's going to have to back off. Someone's going to have to stop going forward. And the sort of complications of the game involve figuring out who that person is. So in a sense, it's a coordination game again, because you have to coordinate on who the person to swerve is. Okay, so that's a chicken game. And now I'm going to look at Stag Hunt, one more game. This game comes from a story in which you are both hunting in I don't know, the King or Queen's forest, and then you can either choose to go for the stag, right, the big game, and get a feast. But that only works if you both cooperate. You both aim go for the stag, or you can go for the hare. And the hare is guaranteed to work for you, but will yield a lower payoff. So what happens? How do we set that up? Well, the best option is when we both go for the stag. So here's the stag and the hare. This is also a hawk-dove game you might have seen in a different context, maybe in biology. So if we both go for the stag, you both get 4. That's the best possible payoff. Oh, sorry, I made it 3. Let me make sure I'm consistent here. Okay. So you both get 3. That's the highest payoff. That's the best possible outcome. Now, if I go for the hare and you go for the stag, I'm okay. I find the hare pretty easily because I'm the only one looking for it. You, however, get nothing because you try to get the stag, you were by yourself, you needed help. Same thing reverse over here. If I go for the stag, I get 0 and you get the hare, which is 2. If you both go for the hare, maybe it's a little harder. It doesn't have to be. The game works with a 2 or 1, but let's say it's 1. Let's say the hare is a little harder to find, but we both find hares and it's okay. This game will work fine if those are 2s as well. It doesn't really matter. What happens here? Well, again, they're going to multiple equilibria. So if you choose stag, I compare 3 to 2. I choose 3. If you choose hare, I compare 0 to 1. I choose 1. If I choose stag, you compare 3 to 2. You choose stag. And if I choose hare, you compare 1 to 0. You choose 1, and there are 2 equilibria again. So again, we have multiple equilibria, and in this case, it's like a coordination game again in the sense that you could either both choose A or both choose B, and both are good for you. In this case, A is much better than B. The slight difference in this game is now there's a difference in risk. If I choose the stag, right, thinking that that's got to be the one you choose because it's the best outcome, and that's got to be focal in some fashion, right? We've got to both agree on the best outcome is the best thing to try. That's great, but I have to be sure that I know that I know that you're going to do that, and you have to be sure that you know that I know that you're going to do that, and so on and so forth. So there has to be a lot of common knowledge and a lot of common belief that we're all going to choose stag. Because if one person fails, and this game works better when there's like 10 people, all who have to choose stag to get the stag. If any one person deviates, no one gets it. But if I think there's any chance that you decide not to go for stag, I get nothing, so that's risky for me. In contrast, I can secure at least 1 by choosing the hare. I maybe get 2. So the hare is an equilibrium that's sort of not as good as the stag is, but it's preferred via risk. It's less risky for me. I suffer less risk by choosing the hare because I can't get the 0 ever than I would by choosing the stag. So there's a little difference in there. For 2 people, it seems okay. And what if I had 100 people playing this game? And the way it worked was if everyone chose the stag, we would all get the best outcome. But if any one person deviated, then no one would get the good outcome. In that case, choosing the stag, even though it got you the best outcome, would require believing that everyone went for it. Whereas choosing a hare is safe. You automatically get something better than 0. So it sort of minimizes risk in that sense. So that's the Stag Hunt game. Just to finish off this fairly long module, this is one of the longer ones, I'm sorry about that. Just to finish off this one, we talk about Cornell Competition. All the stuff we've dealt with so far have discrete outcomes. That's not necessary. We can set up a game that looks like this, where there's 2 players, and each player will end up having some price assigned to that player's good, and some widget or whatever, and some quantity that they produce of that widget, and there's a player 1 and a player 2. And we assume there's some kind of price function that takes the sum total quantity produced and assigns a price to that. We usually assume that the more quantity produced, the lower the price is, because it kind of floods the market. And we assume both players have to use the same price in equilibrium. And each player suffers some marginal cost 0, C, for production. In that case, what's your profit? Well, your profit is the total price, so the price per thing, minus the cost times the amount you produce. And there's one of these for player 1, and there's one of these for player 2. And now we have two different, what are called objective functions. These are payoff utility functions. And we have to maximize them, so the Q that makes this the biggest possible is your best response to your opponent's Q2. So this thing is going to lead to some kind of equilibrium best response that's a function of the other player's action. And this thing is going to give an equilibrium for player 2 that's a function of player 1's action. We'll have simultaneous best responses. An equilibrium is when both players are playing the best responses. This is a system of two equations and two unknowns. It'll produce a solution, and that solution to the system of equations will be the equilibrium production that each corporation, each company should produce, each factory should produce. We're not going to do this in detail here because there's not calculus required for this class, but the same logic you can apply for discrete outcomes can also be applied for continuous outcomes. You just find each individual actor's best response and then simultaneously figure out what the equilibrium is such that each player is simultaneously playing a best response to the other. Okay. That's it. In the next module, we're going to move on to sequential games. Thank you very much.